So, thank you very much for the invitation to be here. So, as Ian said, my name is Scott Collis. I'm working at Argonne National Laboratory in the Environmental Sciences Division, mainly working with the Armed Climate Research Facility, doing remote sensing retrievals of cloud and precipitation physics. And on this title page, it's this is like my why bother type slide. This in a single slide kind of shows what we do. We take radar data, remote sensing measurements, and in-situ measurements, try to make a cloud model type picture here. So this is radar data from our C-band system in Oklahoma. This is rainfall data from an operational weather model. This is actually rainfall at the surface, a rain rate in millimeters per hour. And then we try to link that to what a climate model might see. So this is actually output from the Community Atmospheric Model version 5 that was in the latest ICPP assessment, and we try to link all those scales in order to build a better representation of these physical processes we see in the atmosphere here inside this climate model. So it's all about comparison across scales. And that's kind of the 40,000 foot view. In this talk, I'm going to get much down into the weeds. So there's one thing, and again, I've tried to tailor this talk for what I kind of assume to be a general CI kind of audience here. And one of the things we deal with, which I know gets computation people, computer people excited, but also weather people, is data. Because there's one thing we've got a lot of data. So we all live in the atmosphere. We're actually a walking 1 meter tall-ish sensor for our atmospheric environment. Our phone is picking up atmospheric signals all the time, pressure sensors. Every modern vehicle now is measuring heat. Actually, most modern vehicles have radars in them. So we're actually living in this evolving environment where there are millions of measurements made every second. A small portion of those measurements go into a mathematical expression of atmospheric interaction and is used to build basically a gridded representation of interesting variables: temperature, wind speed, humidity, whether there are any water particles or any aerosol particles there. And then we use partial differential equations to basically progress it to a next step. This could be done for predictive purposes, so Tom can tell us what the weather's going to be next week, but it's also done for us very much from a process level understanding. Looking at a single sensor tells us about that single thing we're measuring. We need a dynamically consistent way to fuse all the measurements together to understand how increased humidity may lead to stronger thunderstorms, how more carbon particulate matter in the atmosphere may lead to more warming, and does that lead to more clouds or less clouds, and so forth. So this is called, so we have observations coming in, we have a constant assimilation cycle, taking in all our measurements, trying to put them consistently on a grid, and a model that runs that we get information out of. So I talk about data. Now I'm a nuts and bolts kind of guy. People start talking big data and all this kind of stuff. It's like meaningless buzzwords unless I know, well, what exactly are we talking about here? I tend to break down data into 4 different types. You have point data, data that is measured from a much smaller sensor than the phenomena you're measuring, that could either be fixed or stationary. A weather sensor measuring temperature, relative humidity and winds. Could be on an aeroplane, so there could also be geospatial information that varies in time from that sensor. A balloon-borne sounding is a very good example of a measurement. We have a big weather balloon, we put a temperature and humidity sensor, and we send it up into the atmosphere to give us information in the vertical, but it actually also kind of advects horizontally in the winds. Another type of data is passive remote sensing. That is where you have a sensor on the ground that is accepting what you give it. It could be measuring sunlight, the spectrum of the sunlight coming in. It could be measuring intensity in the microwave spectrum that can give us some information about line integral type quantities. Basically sensitive to everything in the atmosphere that's come down to us. Another version is active remote sensing. This is where we're no longer just relying on what the atmosphere gives us. We actually throw out some of our own radiation, let it interact with the atmosphere, Am I moving around too much, Rob? And we then look at what comes back. So one of the data sets that I deal a lot with is radars, and I'm going to get on to describing that more. But another thing is a LiDAR. We actually send a little laser beam out into space, into the atmosphere, and then we monitor for returns, and that basically then tells us how that laser beam is interacting with aerosols, clouds, water vapor in the atmosphere, and we're actually able to play a much greater role in changing the frequency of the laser, the width of the laser, measuring the polarized moments of the laser. And this can be broken down into either column, where we basically sit there and look up and just study that column above us, or we actively scan the sensor to try to map out a whole volume of the atmosphere. So these are three examples here. This is actually what's called a two-dimensional video distrometer. It's a camera for raindrops. We basically just take pictures of raindrops as they fall through them. This is what we call a radar wind profiler. Works at 915 megahertz, sends beams of radiation out that scatter off turbulent eddies inside the atmosphere. So we're actually able to measure that turbulence and back out the wind speed as a function of height from that. And this is a naked scanning precipitation radar. Often when you see these radars, they're behind great big golf ball domes that protects them from wind and people literally shooting at them, which is the problem we have in Oklahoma. The technicalities of field work. So, as I mentioned before, I work for the Atmospheric Radiation Measurement Climate Research Facility. It is a terrible, well, wonderful because I work for them, but it is a mouthful and has a lot of historic implications. Was first convened by the Department of Energy to understand radiative transfer in the atmosphere. If you have a source of incoming shortwave radiation in the visible that our eyes are sensitive to from the sun, how does that interact with gaseous species throughout the atmosphere and the land surface to build what we call radiative balance, which simply means heat comes in, heat goes out, and if everything is good, the Earth remains the same unless you start changing CO2 levels and other things in the atmosphere, and that radiative balance is perturbed. Did a very good job. They built one of the most commonly used radiative transfer models for dealing with this, except there was this really pesky things that came around. One of them was aerosols. Aerosols do funky things to incoming radiation, but even worse than aerosols are clouds. Clouds have a catastrophic effect on radiative transfer. Anyone who walks under a cloud, suddenly feels a lot cooler, knows that clouds have a huge impact on Earth's energy balance. And one of the problems is clouds not only affect Earth energy balance, they react to Earth's energy balance. So there is a feedback cycle there to the point that we can't just get along with clouds, make up a nice statistical relationship that ignores the underlying physics. We actually have to understand the underlying physics of clouds. One of the tools we can use to do this are radars. Radar stands for, this isn't a laser pointer, so I better not go like this. Radio detection and ranging. It was first invented as a way for locating big scatterers, aircraft. But they had this really annoying noise signal on there. Whenever it was raining or storming, they had all this noise that hid their aircraft. Well, one man's noise is another man's signal. All it does, this works at a frequency of around about a wavelength of 3 centimeters. So it's in the microwave regime. It puts together a pulse of radiation that is, a couple of tens of meters long, throws it out into the atmosphere, turns on a sensor and watches for what comes back and times that. And by timing it and using the speed of light, you know at which range away from the radar that the signal is coming back. So if I have my aircraft sitting out there, I throw a beam of radiation at it that has a discrete length. I can sit there and wait for it to interact with the plane, and using the timing from that, I know that plane's location. So we use distributed scatterers here. So instead of a plane, it is a cloud of raindrops or a cloud of cloud droplets or ice particles, and as I'll get to later, all kinds of other things. One of the primary things we measure is reflectivity. It literally means how reflective is something. If I send, 250 kilowatts of radiation at it, how much of that radiation gets scattered back? And that is just the number of scatterers times their cross-section. Right? But the cross-section of a scatterer behaves differently when it is a different size compared to the wavelength of the radiation you're using. So this is C-band. This is a 5.4 centimeter wavelength radiation. This is the particle diameter. And this is its cross-section. We can see here that as we increase the particle diameter, it has this lovely log-log relationship. This is fantastic because it means that as I have bigger droplets, I get more radiation scattered back. So by the intensity of these scatter, I can instantly infer something about what I'm scattering off. This is called Rayleigh scattering. When the droplets get very, very large, they go into this terrible resonant behavior. This is called me-scattering. So basically, the reason why ARM has a lot of different wavelength radars is for cloud droplets, which are tiny. We want to get really bright returns, and we know they're tiny, so we know that we don't need to go into this me regime. When we're dealing with precipitating drops, which are on the order of 1 millimeter to about 5 millimeters, we use these longer wavelength radars that are far less sensitive and a lot more expensive and big to build because we want to stay in this linear regime. But what we do is, using a bunch of constants here, we're able to back out this term here that is called equivalent reflectivity factor that is wavelength dependent and roughly comparable against these different frequencies. When you see a map in the news from a radar, or you have the iRadar app on your phone, or you have radar scope, the thing you're looking at is this quantity here. And its physical relationship is the 6th moment of the drop size distribution. If I have a volume, I'll have a PDF, a probability distribution function of drop sizes. Some will be very big, some will be very small. The reflectivity you see is this function here times e to the 6th integrated. So when you see an increase in radar reflectivity, it could be just due to the fact you've got a lot more drops, or it could be just due to a few larger drops that have this to the power of 6 relationship. So now we're kind of now we're actually back in about 1964 when we start talking about radar reflectivity. Here at this very institution where David Atlas and colleagues basically first started investigating the use of weather radar for severe weather detection. They saw the first tornado hook and so forth. Now we're going to step to, probably 70s to 80s, and I'm going to talk about polarimetric. Most radars, they are non-polarimetric. They send out a polarized beam of radiation that has its electric field orientated horizontal to the Earth's surface. The reason why we do that is because as drops fall, drag makes them go oblate. So they end up with a shape like this. So they have the greatest cross-section in the horizontal axis. Putting in a vertical polarization, so here's one of my waveguides here, coming into my horizontal polarization. I have another waveguide here that's sending out a vertical polarization. So now I'm not only able to see reflectivity, I'm able to see differential reflectivity. The difference in reflectivity between the two channels tells me about how oblate or how asymmetric something is. Something called differential propagation phase, which can give me information about the line integral of liquid water I've gone through, and a whole other bunch of really useful things. So why bother? This is radar data from Queensland, Australia, during a very severe thunderstorm event that we've actually just published a paper on. This is reflectivity factor here. This is a cone of information mapped out as my radar spun around like that. This is at 9.1 degrees. This is at, the next one I show will actually be a higher elevation. So we can see here, we've got a very high reflectivity here, but I also have a very high differential reflectivity. This means I'm mainly scattering off big oblate drops. When I go up to a higher tilt now I'm way up at 17.8 degrees. Here, I've got this massive reflectivity signal here, 70 dBz. It's a logarithmic unit, so this is orders of magnitude stronger than the rainfall we see out here. But all of a sudden, I've got no differential reflectivity. what I'm scattering off is no longer different in one axis than it has in the other. So what this actually is, these are very, very, very large hailstones that are actually tumbling as they fall. So on average, they have the same cross-section horizontal as in the vertical. So instantly this has given us information not just about the size distribution, but about the habit, whether we're dealing with ice, hail, or whatever. As I said, we don't just see raindrops with radars. This is actually data that I grabbed 2 days ago because a friend of mine on Facebook said, hey, look at this down in Miami. So this is from the Miami 88D radar. There's a couple of really interesting things here. One, this is raindrops. These are storms coming across there. This beam, you can see here, is the sun rising. The radar, as I said, it sends out its own radiation, but it keeps its sensor open, waiting for returns. So when the sun comes up, all of a sudden there's this background signal in all range gates. And also, what happens in Miami when the sun comes up? The birds go out to eat. So what you can see here is what we call a wrist ring. This is actually all the birds taking off as the sun comes up and spreading out in all directions there. So, talked about radars, talked about measuring the atmosphere. Now I'm going to talk about computation. And I'm going to go off on a little tangent here that probably most of you guys are really familiar with, but as an atmospheric guy, I'm only just learning, and I think it's so cool. So, we've got many, many radars out there. They produce a whole heap of radar formats. I've got European radars, I've got American radars, I've got Japanese radars. But basically, we want to do the same things to them. We want to do corrections in antenna coordinates of range, azimuth, and elevation. I want to map them to a model-like grid that is in X, Y, and height. And I want to do retrievals on them to get from nasty, nasty things like radar reflectivity to things like rain rate, number of drops per cubic meter, wind directions. So what we do with this is we actually build an architecture called the Python ARM Radar Toolkit. And basically all it is a series of ingests and what we call a common data model. The idea about a common data model is just a representation of the data in memory or the particular programming language you're using, which in our case is Python, for the data that is strictly adhered to. So that when I have an algorithm that works on the data, it accepts that common data model and it returns that common data model. It's kind of common practice, but believe you me, it's not followed in our domain-specific community. So the nice thing is by building up this careful infrastructure and writing a whole heap of ingests from different formats, including things like continuous integration and unit testing in our code, we're able to put it together into a package and put it on something like GitHub that then can allow other people to interact with both our radar data that's given out freely by the ARM program, but by the toolkit we put together of the retrievals. So people go, Scott, I really like the way you do your mapping, but your attenuation correction is just terrible. And all I need to say to them is, great, write me a new one. Here's the code I put together. I put the code together in the gridding. All you need to do is fix that tiny little thing that you have an issue with. We can take that domain-specific knowledge and put it back into our toolkit. And so at the moment what our toolkit does, reading and writing of data in the I/O modules, correction of data in the antenna coordinates, mapping to a Cartesian grid, retrieving information from radar moments to geophysical moments, and graphing and visualization. So simple things like being able to plot your data onto a map is really handy. I've loved using GitHub. I've found it to be a great website and a great interaction and methodology for accepting unsolicited code. It's blown me away. So we have 2 people who are funded on this project, myself and a developer who's working with me. We now have 9 people who have contributed code to the projects. Most of our contributors are European. They've picked up our data, our radar software, used it on their radars and come up with better ideas for doing things. Had an idea of putting what we call a pull request. We go, that's really cool, and we accept it. So this is as of, I think it was 2 days ago where we're up to the moment. So there's Jonathan. He hasn't been very busy lately. He's been on travel, so I can't see him. Kirk is a PhD student who's working at McGill with a colleague of mine doing retrievals of 3-dimensional winds. Joe is a guy at CSU who's working with one of their flagship radars down here. I don't even know this guy's real name, but he's from Europe, and he's put together some very nice contributions there. And as you can see, so this is where he's worked on, this is where I worked on a completely different path, where I actually had a problem with some of the map registration. I got that working, put in pull request, and it's gone back into the trunk distribution now. So,
Scott?
yes.
How did they hear about the project? How did they find you on GitHub?
I give talks sometimes, and word of mouth in general. It is, we're very lucky because we actually have a software project that is supported by a DOE sponsor, which means that we can encourage people very strongly who are funded by our agency to work with our software. Because we say, this is a really good path to be able to contribute back in your funding. In the end, a lot of the people from other countries, especially in Europe where they have a much smaller funding pool to draw from, they just like to have a code that works. So a lot of the radar software code it's old and it's almost back in the tape day. So I worked with some mapping code I was talking about called reorder that when you look at the I/O and the way the I/O is handled, it is done sequentially because it expects it to come from a tape. So I'm going to show you some code now because I can. Unfortunately, this is kind of small, but I'll step you through. This is actually taken from the IPython notebook. Anybody who's worked with Python and hasn't checked out the IPython notebook, it is awesome. It runs a Python kernel in the background and connects it to a HTML interface through your browser that allows you to execute code cells and then see the result below the code cell. So what that allows you to do is to put together a scientific notebook that is shareable, and people can also grab it from GitHub, make some changes to your notebook, send it back to you. So here we are. This is actually the import line for PyArt there. Import PyArt, import a whole heap of other software here to do plotting, reading, numerical things, and interact with the operating system here. Here is the file name of that data I showed you with the birds there that I went and grabbed for free off the internet from the National Weather Service. There's the read set. All of a sudden, I have my radar object. That radar object will look the same no matter what the radar it came from. It could come from a European radar, DOE radar, Australian radar. It will just be a radar object. And very simply, to see what fields are in there, I just print radar.field.keys, got differential phase, cross-correlation ratio, spectrum width, reflectivity we talked about before, differential reflectivity, and radial velocity. So I want to go and plot this up. Some simple plotting here. Plotting my differential reflectivity, there's my little roostering there. Plotting the reflectivity there, the roostering there. And my radial velocity here. Radial velocity tells me the speed of the scatterers to and away from the radar. So here I can see on this side, they're coming towards the radar. That side, they're going away from the radar. So they're kind of spreading out like a sphere. I kind of think, I can start to see a signal here. That's interesting. I want a little bit of processing on this. So again, working with our common data model mentality here, all I need to do is put together something that follows my common data model and put it back into the radar. So what I want to do, I'm going to grab my differential reflectivity and I'm going to run, just trust me when I say this bit of code here, this has a 10-point Butterworth smoother over the data. What it actually does, the Butterworth smoothing, but also fixes up the end issue so it's the same length as the data we're dealing with before, and put that back into my common data model. The joy of this is once I do this, this data will actually work with all my other routines. The plotting and stuff like that will just work. So now you can see here I've changed differential reflectivity for differential reflectivity smooth. So now I can start to see a really nice signal in there. So let's zoom in on that. Again, this is our roostering signal from before. Here's my radial velocity here. Birds coming towards, birds going away, birds going that way, birds going that way with zero radial velocity because they're going at right angles to my radar beam. And I can see here, this has a really negative differential reflectivity here. So I'm getting more returns in my vertical channel than my horizontal channel at these sides here where I can see the birds going across the radar beam. And here I have a slightly positive, when they're going towards or away from my radar beam, a slightly positive differential reflectivity. So why? Why do we think that? Birds kind of look like this. Actually, I looked into this, and these are from the Everglades, so these are actually big birds. So this is a bird's side on. You can see here, they have a much larger axis ratio that way. And there's tail on there. So these give me my negative differential reflectivity when they're traveling that way, and positive when they're coming there. That's kind of a simplistic approach, because I said this is crowdsourced. I literally did this yesterday on Facebook. Yes?
Would you say we need to, this is fascinating.
Oh, sorry. How long have I got left?
I don't know. How is it, I think we're trying to
Like
get 2 in.
5 minutes?
5 minutes?
5 minutes? Good.
How is it that that one is negative and one is positive? I can see where there would be a difference, but not that one would become negative.
So what it is so my reflectivity, if I have a negative differential reflectivity, it means that the reflectivity in the vertical is actually greater than the reflectivity horizontal. It's a difference, exactly. So basically, our software here is to bridge the gap between radar science, which is across here, and the whole Python infrastructure. So things like scientific Python, numerical Python, and Matplotlib, which does all our plotting. Another example we can use is linear programming here. So we've got the signal here, which is our propagation phase, and we want to get rid of these spikes here. We can do basically a constrained fit there using an existing linear programming algorithm. So I'll skip through that in the interest of time. So this is an example of a rainfall retrieval from one of our radars, millimeters per hour. Now we're dealing with drops and not birds. I'm a lot more comfortable here. Millimeters per hour over a distance on a grid scale that's comparable with a climate model. So we actually did, so this is actually our plot of our southern Great Plains site here. There's our main radar in the middle. That's that 100 kilometer range here. We actually have a whole network of drop sensors, rain gauges, that allows us to also not only do our retrievals, but validate our retrievals here. This is our rain gauge accumulation and our radar rain accumulation here. And we can see, because you're comparing an aerial average of a 1 kilometer grid cell to a point, you're going to get some spread, whether you're on the edge of a rain cell or in the middle. But we have this spread, we also have a non-biased measurement. The actual bias in this is very, very small. So we have confidence in our rainfall retrieval. One of the other retrievals we can do from our radars, you saw with the birds, I showed you radial velocity, right? So we have 2 or more radars. What we can do is we can use these radial velocities in as constraints in a retrieval of U, V, and W. So the meridional, the X component, Y component, and Z component of the wind speed here. So basically we put that into a conjugate gradient solver as a cost function, and we solve that cost function for my wind speeds. So this is coming from C-band radars in Darwin, but also we can do this in Oklahoma with a network of X-band shorter wavelength radars that we've got there. And what we get out in the end is basically grid. This is actually an example of a score line that went through Darwin during 2006. The slices of reflectivity, and these vectors here show our retrieved winds. We've got a nice updraft coming in front of the downdraft and precipitation signature there. But this is really interesting for me just from a pretty picture point of view. What we want to do is we want to build statistics of this, because only when we have enough statistics to get past the stochasticity of the atmosphere can we expect to make it comparable to climate models. We also need to do validation work, so we actually had a separate profiler system like this that actually sat in our retrieval area here that were able to do comparisons between our retrieval from the radar and retrieval from the profiler, and we got this very nice relationship that basically showed besides some difference in sampling volume, we saw the same thing. And then what we're able to do is do a statistics of vertical velocity over 2 weeks worth of data to work out where are our larger updrafts in our storm systems, where are our smaller updrafts, what's our 99th percentile vertical velocity in the atmosphere, and what is, say, our mean 50th percentile vertical velocity. Why do we bother doing this? Because we can do exactly the same kind of exercise using fine-scale models and climate models. And when we do, that's what they come up with for this same data set. These massive 20 meter per second vertical velocities that when you compare to our measurements, they're much, much hotter. And so we're actually helping geophysical fluid dynamics laboratory and people working on the latest climate models work out why are we seeing these stronger vertical velocities in their models compared to what we're seeing with our radars. So Very quick slide on open science and reproducibility. This is an example of an IPython notebook here. All the work we do, we put onto GitHub in our IPython notebook so people are able to pick it up. And basically, rather than reinvent the work we've done, including the code and the technical details, they're able to start from where we left off. And also, the other thing is, I really want to know when I'm wrong. I kind of go forth into research, and if we knew what we were doing, it would not be called research. So I'm going to make mistakes all the time. The more people that see my work, the more often I can be picked up on what I'm doing wrong. So, what's our take-home messages? Our team's missions are representations of the atmosphere out of observation. The best way to tackle the data diversity problem, the best way to do this is to tackle the data diversity problem first, and build an architecture that allows domain experts and others quick access to the data in a good computing environment. Our experience in open source and social coding has been very positive. The work we did to get the code out there to make it robust has paid off. We have lines of code that has made our algorithms, our retrievals, our work for our DoD sponsor better by doing this. We have more data than we know what to do with. So one of the reasons why I'm interested in the computation research in the University of Chicago, in the geophysics group, mathematics and computer science groups, is that I want to build relationships, postdocs, students, come work with our data, work within our toolkit, and see what we can achieve together. Because most of our best advancements in radar meteorology have nothing to do with radar meteorology, much more often signal processing, engineering, and computation. And no real time there, but the demo I showed you with the birds, it's all online there. You can download and look at the IPython notebook online there. So thank you very much. Sorry for going over time.
No, it's okay. It would be great to learn even more about it.
Any questions or comments while we're...
Yes, Rob.
Sounds like the I/O part is the most important, because that's when you translate the varied formats into the common.
Exactly. So you're right, it's the most important, and that's where most of our lines of code are. In general, the ideal thing, and this has happened a couple of times, is that we would encourage people who wanted to work with our toolkit to write that ingest themselves. We basically have a recipe for how to do it, how the data looks. So we've had an example already that Joe Harden, one of the things he's working on now is an ingest for this very advanced radar in Colorado, that once he writes that ingest, he has access to everything else that's in the toolkit. But you are right.
Are there any radars with a format that's completely closed, you want to get to it, but you can't?
To be honest, I have the luxury of telling them to hit the road if that's the case. This is open source software. People can take and do whatever they want with it. But unless they're going to share code, they're not going to get any help. You all good?
Thank you very much.
No worries.